Well, good morning. Welcome to Spain, to Madrid, to the Real Academia de Ciencias de España. I am Miguel Alario Franco. I'm a member of the European Academy of Sciences since 2018, I think. And I'm very pleased to have the opportunity of having the General Assembly in Madrid. We have, as an academy, a certain tradition, scientific and historical, and our president, Professor Sanz Serna, that will speak later. He will give you some details about the history of the academy. In fact, in the last meeting in Brussels, we were having scientific discussions, and then when the point arrived to discuss the site for the next assembly, I suggested this Madrid, and happily enough, these gentlemen and ladies accepted that be here, and today is the culmination of this thing. And this event, I hope, is going to be interesting for all of you that have came from far away, and I hope that you will get something out of the meeting. This is not really a ceremony, it's just a presentation. The other people is going to intervene for a while and just informing you of the events along the day. You have, everybody has the booklet and the program, so I think that just give the word to Professor Rodrigo Martins, our president.
Saints.
Pardon me?
It will be.
Oh, okay. Well, then Professor Sanz Serna is a mathematician. Probably most of you know him. He's a member of the European Academy and is the president of this academy. Please.
Dear President and dear colleagues, Professor Alario has already welcomed you in Madrid, and in particular to this academy. And maybe I can also welcome you again, a second welcome. And please, on behalf of the Academy, make yourself at home. And I hope the Academy provides you everything you need during these 2 days that you will be here with us. Professor Alario has suggested that I tell you about the history of this academy, but I will be very brief. The academy was founded in February 1847. So last year we had our 175th birthday, and it's a very small academy. It comprises all sciences, so geology, biochemistry, and natural sciences, chemistry, physics, mathematics, computer science. And so it's a very varied by law. The number of academicians is kept very small. So being a mathematician, as in many other similar institutions, is for life, and it's not until someone sadly passes away that we can appoint a new member of the academy. We are very happy to have you here. Let me thank the organizing committee and the employees of the academy for all the work that they've carried out, setting up this conference. And again, if you need something of the academy or of myself, don't hesitate to let us know. Thank you very much.
So, first of all, I would like to thanks to all of you to come to Madrid and to attend to this our annual symposium and ceremony meeting that we will be comprised 2 days. And for all of this, I would like to first to thank Professor Sanz that allow us to organize in this beautiful place our meeting, as well as to the committee that is chaired by Professor Miguel Alario, and also Professor Carpintero Santamaria. So the idea of the meeting and what we try to really to converge today is to discuss something that is really challenge for all of us, which is the energy. So we try to see how this will impact and will be a challenge for all of us, and as a society, as academicians, we have to provide routes and ways where we can really try to impact on our society and mainly on the political decisions that we are taking in Europe. We are Europeans, so we, of course, most of our commitments will impact globally, but of course we have to share with the policymakers in Europe what could be the strategy. The strategy of the Academy is to networking with the political decision makers. We start trying to do this 4 years ago, just in a meeting that we also organized here in Madrid. But unfortunately, due to the pandemic times, we could not do it. But this is what we want to pursue. We want to pursue connections at the European level, and because more and more the political decision should be grounded on the scientific evidence. And this is what we want to, in somehow, to contribute for a better Europe, starting, of course, from our nations, from our regions, from where we belong. And for this, the strategy of the Academy is to speak with all the academies and try to make agreements. At that time when we start making this type of strategy, we signed an agreement with the Portuguese, with Lisbon Academy of Science. We signed this type of agreement, but we could not really improve it. We also started doing the same here in Spain. So we aim to also to have a strategy that could impact on all of ours. And moreover, as we are a global academy, we have also to see how we could make bridges with all the continents, so going from Asia to the Americas. And this is something that we aim to do, but first of all, we want to consolidate our position inside Europe. And we are very glad because we could be promoting. We are not a close society as it is this academy in most of the European academies, but we aim to keep on going with this strategy. And in this strategy, we are speaking with all the academies, starting from what I call peripheral regions. And for this, because we have to think as Europe as a whole, not just the European Union, but Europe as a whole. And in this sense, we will keep on going and trying to fight for this strategy. Of course, we are glad from having our fellows coming from USA and also from China. And more we want to discuss the matters that will impact on our lives for the future. And for this, I have to say that we start already a strategy. With China, with Chinese Academy of Science, in the area of the oceans and the earth, we will organize in the European Parliament 2 weeks from now, I believe, a meeting in the European Parliament where we will speak. So we will have Paul Tregerer speaking from us, and he belongs to the Earth Division. And this is something that is globally very, very positive. We organized last month in China a meeting where we tried to see how materials could impact, and also the strategy goes through the energy, so mainly on how we can storage energy. And this was a very positive meeting that we organized, and we have been there. So with the representatives of our academies, we were 5 people from the academies, and this is our strategy, to get in touch. And also, of course, we want to promote and to be all of you that are members and fellows of the Academy, to be a voice in your countries, to be a voice in Europe, and try to use the Academy to promote also your initiatives. This is what we think we need to strengthen behind it. And of course, the strategy is to go close to the policymakers, which means close to the Minister of Science and Technologies and try to see how we can really play a role in this grounds of science for all. So saying so, thanks to all of you to stay here, and I gave the word now to Professor Alain for
Maybe you want to say something? Okay. Good morning, everyone. So my name is Alain Tressaud. I am the Vice President of the Academy, and I am very glad to see you here to listen for very important talk. And it's a pleasure for me to be here. Last year I was already once in Madrid for the birthday of my colleague and friend Miguel, and it's always a pleasure to be here in your so beautiful city and country. So I will introduce the speakers of this first session, and this first session will be devoted to see with some examples how catalysis and chemistry could change the energy world. And it's a very important topic, of course. So we will just start with the first speaker. So the first speaker, Professor Hermenegildo Garcia from Universidad Politécnica de Valencia, and Mr. Garcia will speak on photocatalysis and how to produce fuels from sunlight. What a fantastic title. So please.
Well, as Alain has already said, catalysis has always been behind energy, producing fuels, producing oil, and it has been... Okay. But this is not... This is... Okay, now it's better. Sorry. The other was more interesting. But anyway, yes. So thank you, Miguel, for the invitation and also the organizing committee. So catalysis has been just producing fuels, and what we are going to hear now and also the next talk is other type of catalysis, because catalysis should be really called thermal catalysis. Thermal catalysis means that to have the energy that is needed to overcome the transition state, we need an energy. And typically, until now, catalysis has been given this energy by heating. And heating means burning fuels and other things. But now we are just thinking in other type of catalysis, in where instead of heating, what we are going to do is to provide energy in a different way. And this different way is going to be just sunlight using photons. And first I will introduce briefly the topic, but the key point of my talk is this. Natural photosynthesis has been providing for many years for all life, all the fuels, and now we are coming back to this idea and how natural photosynthesis has controlled also the climate in the Earth and has controlled how the Earth has been charged with energy, chemical energy, and now we will move towards artificial photosynthesis with the production of solar fuels and some conclusions. Yes. So I was trying to put some new data, but really these are the last data that we have now. They refer to 2020. And when we pay attention to the contribution of all the primary sources to the energy, what we realize is that still in 2020, about 80% of the energy that we are consuming are fossil fuels, natural gas, oil, and coals. And we are using these fossil fuels by burning, and burning these fossil fuels produce CO2, and actually the amount that we consume per year is incredible, it's very large. It's in exajoules, that is 10 to the 18th power. And if we count just by second, and we count the power that we need is about this, 6.6. This number, just please keep in mind, because later I will show you sunlight, how much power can give us. And the power that sunlight can give us is much higher than this value. But this is just for 2020. And what happens is that as consequence of burning these fuels, CO2 is changing. CO2 has been changing over the many thousands of years, and we have just a maximum amount of CO2 that is about 250 ppm, and a minimum amount about 200 ppm. So CO2 in the atmosphere has been fluctuating over years, and we know this because we went to the North Pole and we took the ice there, and the ice, this is a perennial ice, and just by dipping inside the ice we know exactly how much CO2 was at that time. And this fluctuation coincides with periods in where the climate was hot and also periods in where the climate was cold. But have a look to this, we are just in this, and we have raised at the sky of 450 ppm. So what is going to happen if this was hot times, what is happening with these values? And the models predict that the climate is going to change, and this is just really a big problem. So just paying attention to the last 60 years, there has been an increase, a jump from 300 ppm to over 400 ppm. And actually, the amount of CO2 that is in the atmosphere is not that large compared to the amount that we are just dumping there. So the total amount of CO2 in the Earth is estimated in 3,000 gigatons. And we, every year, are introducing more CO2. And the amount that we introduce is 40 gigatons per year. So this is about 1 or 2% of the total amount. So it's a very large contribution. And this contribution is due to the combustion of fossil fuels, coal, that has 30%, oil, natural gas, and also here some other human activities that are also changing and contributing to the change in the CO2 percentage, that is deforestation and also other industries like cement and so on. And we are just concentrating on CO2 in the atmosphere, but CO2 is not only in the atmosphere. Particularly, we have to pay attention that CO2 is also in the ocean. And because CO2 is an acid, when CO2 dissolves in the ocean, will change the pH. Typically, a natural pH in the ocean is about 6.8, something like neutral, but with CO2, we are changing the pH to the acidic. And this will have consequences that we still have no model for this, and we still have to wait for these consequences. So, and we know that this CO2 actually comes from the burning the fossil fuels. And the scientific way to determine this is because the percentage of carbon-13 that we have in the oil, because the oil has been just over many millions of years under the earth, the percentage of carbon-13 is very low. It's very low. And when we see this plot, what it's telling us is that we are just decreasing the percentage of carbon-13 in the CO2, this isotope. This means that we are just contributing a lot by burning, introducing new CO2 that has a depletion on the percentage of CO2. So we know that this is obvious, because actually we are using, just in Spain, 40 millions of barrels per day of oil, and we are just burning this oil. So what happens with photosynthesis? Well, photosynthesis is the reaction in where we use sunlight. Well, the plants, the green plants, they are using sunlight, and with this sunlight and carbon dioxide and water, they are producing carbohydrates and oxygen. So this is photosynthesis. But when we consider in a different way this process, really the Earth, what it's doing is charging like a battery. Because what we are doing is just reducing, CO2 is the most oxidized form of carbon, and we are producing carbohydrates that they are reduced species. So here in the cathode, we are producing some reduced carbon species, carbohydrates. And then in the anode, what we produce is oxygen. And actually, the presence of oxygen in the Earth is unique, because no other planet has oxygen in the Earth. So we are just like charging this battery with the sunlight. But what happens is that this battery of the Earth has been charged for many millions of years, 2,500 millions of years. But the humans that they are here, like this lamp, are discharging this battery incredibly fast. So this is a paper that I recommend to read from Stransky in a different perspective, saying that over many years we have produced these fuels, and these fuels, they are there. Now we are using them very fast, and then in 500 years we will discharge completely the battery. This means that we will not have oxygen and we will have only CO2. And this we know because if we compare the Earth with the other planets that are near the Earth, Venus, for instance, the temperature here is too hot, 420, it's very close to the sun. But the atmosphere contains CO2. It says 96%. So Venus has carbon, but the carbon is a CO2, because there is not something that has charged this, has reduced this CO2 to something that is carbohydrate. But if we go to Mars, then because it's farther from the sun, the temperature is very low, minus 50 degrees. And here, there is no atmosphere at all. But CO2 is present just because it's just in the solid state in Mars. So CO2 is present in all the planets, in Venus, and is present in Mars. Where is oxygen? No, there is no oxygen, because unfortunately, natural photosynthesis has not operated in these planets, and for this reason, there has not been a chemical potential that has been charged. So here in the Earth, what we have is only a very small amount of CO2. So very strange compared to this. And the temperature is there. Okay, so basically the message of this transparency is that natural photosynthesis has generated here a chemical potential that has allowed the life, has allowed the human's activities. And what happened is that we are abusing of this potential, chemical potential. We are abusing so much that we are discharging that fast that this is not sustainable. So the key word here that we should use is sustainability. Sustainability, and this is not sustainable because the human activities are just influencing that much the Earth. So in a different way, we can consider what is the role of CO2, what is changing the CO2, how CO2 is making the global warming. And here we have two parts in the slide. One part is just the day, and the other part is the night. So during the day, what happens? During the day, we have sun, and the sun is heating, and there are many physical phenomena that happen in the atmosphere, and also many chemical phenomena that happen on the surface. And the conclusion is that we are just heating the surface of the Earth. But during the night, this surface that is hot is is emitting heat in the forms of infrared radiation, and this infrared radiation should go out of the planet. But if the planet contains nitrogen and oxygen, because they don't absorb at all in the infrared, this is transparent. If we have oxygen and we have nitrogen, there is no greenhouse effect. But if we have other molecules, like water, that is able to absorb in the infrared, then this molecule, like water, can absorb this infrared and just emit towards the Earth again. And this is the natural way that the Earth has been working. But now, what we are just is dumping in the atmosphere CO2 that has also a very strong absorption in the infrared. So then this light is absorbed and then is reverted. So for this, we are just heating the planet, and this is what the models says, that there is a relationship between the greenhouse emission and the temperature. And the models may have also some discrepancy and may have also some error. They are models. They predict that depending on the year, if we continue the tendency of the emission of CO2, we will reach just a emission of 60 gigatons for CO2. The temperature will increase 2 degrees. This temperature increase is impossible to sustain, because then some ice will melt, the sea level will increase, things like that. So there was an agreement in Paris just to decrease CO2 emissions. Before, in Kyoto, there was also some attempt to decrease this CO2 emission by an agreement between all the countries. But this clearly is unsatisfactory. And then in the Paris, there was a very ambitious plan to decrease this to the values that we have in 1970. This should be achieved by 2030. Look, it's only 6 years. Are we going to achieve this value? And the answer probably is no. This was too ambitious, but we should try to reach this value, and in 2050 it will be just 0 emissions in the EU. So with these models, if we just go to this, what happens is that then the temperature at the end of this century will increase only 1.5 degrees. 1.5 degrees of increase in temperature will have consequences, but will have much less than if the temperature increases much higher. So then the conclusion of all this is that we have to move away from the conventional use of fossil fuels. The President has already mentioned this, and this is a big challenge. And it's even bigger because we don't have time. We don't have time to achieve this target. So it's clear that this will be the middle of the century. And what is going to happen with all the CO2? Just here we have a number that 1 ppm corresponds to 7.8 gigatons of CO2 emissions. So this means that every year we are increasing about 5 ppms or 4 ppms the amount of CO2 per year. So what to do then? So energy has to be affordable, has to be abundant, has to be cheap. We all know what are the just adjectives that we want to use for energy, and then we have to pay attention to the sun energy. And when you look at this number, at the beginning I told you, please remember 6.6 terawatts. That is the total consume of the humankind that we need. 6.6 terawatts, when we compare with this number, is nothing. So this means that if we are able, if we develop science, if we develop technology to take use of sun energy, then we have more than enough. And this is the amount that reaches the Earth, and this is number 4.7 is really the number that we are really going to need for the humanity. So it's a very small amount, less than 1 every 10,000 of this energy that is sending us by sun. And actually, all the photosynthesis is in the Earth, that this is life. All the life depends on 78. 78 of this number is almost also a very small amount. So we have more than enough energy, but how to use solar energy? How to use solar energy? We have already some matured technologies, for instance, windmills, wind turbines, or photovoltaics. But is there any other way to use solar energy for doing something? And our idea, our vision is just this leaf. Can we do artificial leaves? There was an article published in Science, is how far and how close are we to have an artificial leaf? And this will be really the target. It's just to ourselves to produce oxygen, but also to reduce CO2 from the atmosphere. And the answer to this question, how far are we, is we are very far. And we are not going to achieve this target in 6 years, this is for sure. So what is solar fuel? The definition of solar fuel was just very old, from the 70s. This was Anne Moore and Tom Moore, who defined solar fuels as chemical compounds that using solar light can be used for transportation and any other use. Because what's happening is that we cannot use directly solar light for many things. Why? Because solar light depends on the day and night. We don't have solar light at night. Depends also on the weather conditions. But the important thing is that solar light, the power of solar light per square meter is very low. It's very low. We cannot move a car with solar light. This is not realistic. So for this, we need a chemical compound. We need to concentrate many photons. We need to concentrate the sun energy in something that really is a chemical compound. And for this reason, it's going to be a fuel that comes from the sun. And natural photosynthesis is considered by the European Union as a solar fuel because they are using natural photosynthesis, and then they produce biomass that we can use. And according to the European Union, this is a zero CO2 footprint. So the footprint of using biomass is 0 because the plant has already taken CO2. So the concept here is circularity. If you take CO2 and then you produce CO2, the same amount, no problem. This does not change anything. The problem is that we are taking from the underground oil that is in a very low cycle of CO2 and burning it and introducing in a very short time incredible amount of CO2. So biomass, there is no problem. This is a solar fuel and has zero CO2 emissions footprint. But has some other problems. The main problem is the slow growth, and you need to treat pests, and depends on the weather. So, and soil, for instance, it has been calculated that the energy of Italy, this is also an important paper, the energy of Italy, if you plant off all Italy just to produce the energy that Italy requires, is impossible. It's impossible. You need an extra land. So here, the soil is also a very requirement that has to be considered. So natural photosynthesis has a role, very important, but it's not going to solve our problem of energy. What about this artificial photosynthesis? And this is just the topic of this presentation of my talk. And with artificial photosynthesis, we may have several targets. One target is using water and produce hydrogen. This can be done also, probably in the next talk, the next speaker will introduce this with electrical energy. And in one slide, I will compare photocatalysis and electrocatalysis. But certainly, using hydrogen and from water is a solution that can be done. But hydrogen has many other problems related to how to store hydrogen, how to use hydrogen. So what about other chemicals? For instance, with CO2, we can produce other chemicals, and particularly one chemical that will be very, very interesting will be methanol. Methanol, if we reduce CO2 selectively to methanol, this could be a very good, a very interesting solar fuels. Other fuels could be formic acid. Formic acid, so with CO2 we can produce different solar fuels. And then another possibility will be the nitrogen fixation, because the problem of CO2 is how to capture CO2. If we have some source of CO2, we can go there and use this CO2 because it's in a source. But the problem is that the real solution will be to capture CO2 from the air. This is called direct capture of CO2. And this really is a problem because the concentration of CO2 in the air is very low. So for this reason, one solution, what is in the air, is nitrogen. Can we make a chemical, a fuel from nitrogen? And the answer is yes. This is ammonia, has been done, is done in very large amounts. But the point is, can we do this without using heat? Can we do this without using fossil fuels to produce heat? And this is artificial photosynthesis for ammonia fixation. So here I have a slide, is just to compare hydrogen generation by electrolysis and photocatalysis. And so now chemistry is moving to different types of catalysis. One way to promote a reaction is to have a potential different voltage that can promote the chemical reaction. But even for this, you need a catalyst. So this is electrocatalysis, just to reduce the overpotential and to increase the rate in where the chemical is formed. So this is electrocatalysis, and this electrocatalysis is a mature technology that can be used already now. Here the efficiency is about 60%, and this is a plant from Total, an air liquid of electrolysis in where they can produce hydrogen. So this is already established. And of course, there are several things that can be improved. 60% is not 100%. The other thing that is one problem of electrolysis is the price. Because here, one electrolyzer of 1 kilowatt has a cost of 1,000 euros approximately. So here, the equipment is very expensive. Not only this, this was considered the solution when the electricity price was very low, because this slide was thinking that the cost of electricity is going to be zero. Why? Because we will produce so much electricity that nobody will use, so this surplus of electricity can be used to produce hydrogen. What is the cost of electricity? Zero. But here in Spain, the cost of electricity has gone up and has risen to 300 euros the megawatt. 300 euros the megawatt determines what is the price of this hydrogen. It's going to be very, very high. It's not only because you have to spend in facilities. is not only because you have to spend in the electrolyzer, but also because electricity is not cheap. So one alternative could be photocatalysis. Photocatalysis, we are going to use directly one photon, the photon in the visible, to produce the chemical. So, but what is the difference? The difference is that here the efficiency is 60%, while here the efficiency is 1%. So I want to compare this. You can just visually determine how simple is photocatalytic technology. We only need here a surface. In the surface, we put the photocatalyst. Just before, Amelia was telling me that they are using in this type of coatings in producing these glasses. These glasses, just one glass that is exposed, water is flowing through it, and we are producing hydrogen and oxygen. So this compared to electrolysis, in where you need electrical contacts, you need to have a converter to have a continuous current, you need also platinum, you need electrodes. So this compared to this has a very difference. So the price of one photoreactor is much more cheaper than this. But the problem is efficiency. So I tell to my students, look, what do you want to do? You want to study something that is already known and then increase 1%? Okay, 1% is important. It's important, it's a big target. But this is a technology that is mature. Or you want to do something that is disruptive, something that does not exist, because 1% you can consider that is zero. 1%, what is 1%? Nothing. Yes, you have seen hydrogen, but what is the practicality of this? Nothing. So here, my message here is that we have a lot of work to do. This includes basic knowledge, this includes science, this includes technology. So if you have to bet, I think that this will grow much faster than this, because this is already mature. Here the problem is that electricity has to be very cheap, and at the moment electricity is not cheap. So companies come to me, and before they were just clear that they were going to install this electrolyzer. But now they come to me and say, have you any progress? Yes, because now electrolyzers, they know that the price is very high. So if this solution is already ready, if this is known, if this is ready, why don't we have hydrogen now? This is known, this works. Look the plant. So why don't we have hydrogen now? And the answer is because this hydrogen is very expensive. What is the price? The price is about 10 euros kilogram. While hydrogen now, the price is 3 euros kilogram, from 10 to 3. So we know how to produce this, but the price is 3 times higher. So now European Union has created a bank to pay. And they say, you are producing green hydrogen, okay, what is your price? 10 euros, I will pay 7. But this is a bank. This is something that is temporary. It's like a subsidy. They are subsidizing hydrogen, but we cannot continuously subsidizing hydrogen. So really my message is that we have to explore other technologies. We have to explore and develop other science, because then the potential could be high. So we have been working in photocatalysis for many years, and we have been studying many solids that are able to absorb the photon and produce some chemical potential. But I am going to concentrate today in this type of solids. They are called metal organic frameworks, and they are hybrid solids. Before Ronaldo was telling me, I consider myself inorganic chemist. So this is inorganic chemist because you have metal ions. I consider myself organic chemist, and this is organic chemistry because here we have some organic linker. And the combination of the two, you and me, produce this material that the important thing of this material is functionality, because for inorganic chemists sometimes it's very difficult to adapt exactly what is the energy, the band gap, what is the potential. For inorganic chemistry it has been very difficult just to tune the solid, to modify the properties. But for organic chemistry, this is very simple. You introduce a substituent, you make a reaction, you change, so organic synthesis allows to prepare many different organic linkers. So these materials are very interesting for many reasons, but one curiosity of this material is that this material is the record of lowest framework density. What does it mean? The atoms, the mass that we have per unit cell, the mass that you have per unit cell is the lowest at the moment. So these materials are interesting for this. It's like making a building, but making a building only with pillars and joints, no walls at all. For this reason, because this is almost an empty space, actually there are many metal organic frameworks in where the empty space of the material is about 90%. So we have something that is empty. And this allows us many possibilities to introduce here things. But for us, for photocatalysis, the important thing is how can we make responsible to the photons? How can we make absorbing photons and make a chemical reaction? How can we do this? And the answer for this is that with the organic linkers, we will absorb the photons. We have many dyes. We have actually all the colors made by organic compounds. So we will absorb the photon here in the organic linker. And the reaction will occur here in the metal ion, because metal ions are very good catalyst. So the combination of the two is very interesting. So MOFs as photocatalyst, and this is the basic principle of photocatalysis, is that one photon comes and is absorbed, and the photon is energy, and the photon is absorbed here in the organic linker. So photon is just pure energy. And when the molecule absorbs this photon, what happens with this energy? This energy has to do something. And what happens is that this produces an excited state of this, an electronic excited state. And because it's an electron that is excited, it has the opportunity of the electron to jump from this part, that is the organic linker, to this part, that is the metal ion. The metal ion, this is a cation, and the cation is positive, and they like electrons. So this process, in a certain way, is natural because the linker is electron rich, and the cation, the metal cation, is electron poor. So they want electrons. And what we are doing is just pushing it with a little bit of photon, pushing it with a little bit of energy. And this push makes this, the electron jumping from here to there. And this is the key, the elementary step, the most important one in photocatalysis, because at that point, what we have is what is called charge separation. Charge separation is one electron here that is going to do a reduction, electrons reduce, and here we have a hole, a positive charge, that is going to do an oxidation. So with this simple model, we can do reductions and oxidations. This is an electrochemical reaction. Yes, we can do electrochemical reactions, but at the nanometric scale, at the minimum scale, the distance from here to there is a few angstroms, and we are going to oxidize here and to reduce there, but the distance is so close, so this actually could be a problem that is different. But the interesting thing of these materials is that we can modify many things here to increase the photocatalytic activity, because don't forget that I have already said that this photocatalysis at the moment the efficiency is 1%, so basically 0. So we have to improve a lot the efficiency. And we can improve the efficiency in different ways in this system. We can control what is the nature of the metal. Depending on the metal that we have here, we have higher response. And I will show you examples of this. We can also control what is the organic linker. And by controlling the organic linker, I can increase also the efficiency, because the target is going from 1% to 100%. 100%, so increase. So we have to increase this, and one possibility is to just find the organic linker. And also we can use this empty space, and we can put here a co-catalyst. Photocatalysis, co-catalyst, this topic is catalysis. So we always need something to promote a reaction. And here we can introduce a co-catalyst. We have a metal, but we can introduce another metal. And this another metal increases charge separation and increases the efficiency of the reaction. But also one thing that we are now understanding is the effects. The effects. Catalysis is always related with the effects. Sometimes the catalytic activity depends only in a very small part of the solid. You have a solid and the solid is inert. But if you have an atom that is insaturated, this atom that is insaturated, this is the key point in the catalysis. This is the effect. And actually here in D we have a defect. And look at this. Here we have a metal ion that has no linker. So this metal ion has open positions and can react much faster. Here we have the same metal ion, but this metal ion is coordinated, fully coordinated, so has lower reactivity. While here, if we generate these effects, we have higher reactivity. So we have modified all these things, trying to increase the efficiency of the reaction. And we have increased the efficiency of the reaction, but not sufficient. So, for instance, the simple case is this one. This, you don't see the number, but this is 2010. So we started this research 13 years ago, long time ago. And we were the first reporting that this MOF, that is called UIO66, is able to generate hydrogen from water. So this is the metals, and this is the linker. The organic part is this is the metal, and when you form the material that is UIO66 has here the metals and the linkers, and this is just the lattice. But in this linker, we can simply introduce an amino group in red. It's very silly, very stupid. No, this is an innocent linker. No, because when you have a look to this, if we introduce the amino, we introduce an absorption band. Absorption band here in the visible. What is an absorption band? Absorption band means that now the material is able to absorb photons. This is an absorption band. These photons are absorbed. And before the amino group, there was not absorption there. So these photons were not absorbed. But now introducing this, nothing changes. So the structure is the same, the material is the same, everything is the same, but a big difference. It's not innocent. Now we have a band that absorbs photons in the visible. And as consequence of this, then the hydrogen production is 5 times higher than without the amino group. Without amino group, we are producing hydrogen. But with the amino group, we produce 5 times higher. If we go from 1% to 5%, keep this number, is important because 5% is just the limit to have something commercial. We can apply this technology if we produce something that is 5%. Other case, we can modify the linkers and we can put more than one linker. So we start with this. This is UIO66, 68, and this is octahedra. This is the electron microscopy image of the material, and this is just in yellow because this is the terphenyl linker. If we change this linker for this other has the same shape, everything is the same. But organic chemistry allows me to prepare other materials, other linkers, very similar in size and in properties. But now look the color. This is pink because the material was white. White means no absorption in the visible. But if we replace this linker by this, then the material is pink. Pink means absorption in the visible. So, and we can do this starting with this material and just putting in contact with this linker, and this spontaneously is changing from one to the other. And here is the images. We start with this, the UIO68, and we put this linker that is different but very similar to this one, and then the material starts to become pink, pink, increasingly pink. But because it absorbs light, this is absorption, it can also emit. And at the beginning, the material emits in the blue. Because it's white, it emits in the blue. But if you progress and you exchange this linker by this other, then the material emits in the red. So there is a red emission. So something as simple as putting nitrogen. When we put nitrogen atoms, but then the photochemical properties, the light absorption of the material changes completely. And we go from white to pink, and we have emission from blue to red. And the interesting thing is that at one point, that is here in this cartoon, at one point that corresponds to this state, what we have is really like 2 different solids. One solid is the core, and the core is yellow, and the core contains the original linkers. But the external surface, because the exchange progresses from the exterior to the interior, the external surface here, that is pink, contains the new linker. So at one time, it's like having 2 different materials, one in the core and the other in the exterior. And this is known in photocatalysis. This is called junction. This comes also from photovoltaics. A junction is when you have a silicon doped with nitrogen, another silicon doped with phosphorus, and then you have the 2 in contact, and this is a junction. So here in photocatalysis we can also make a junction of two different materials, and we can do this in MOFs. We can control the metal content. So we can start from this MOF that is UiO 66, zirconium, and then we can introduce other metals like cerium and titanium. Not only this, we can introduce this metal in the amounts, optimal amounts, and then the catalytic activity increases, and we can multiply the production of hydrogen by a factor of about 6 or 7. Also, co-catalyst, we can use this MOF that is MIL 125 amino, and then we can use these cavities to introduce two different metals, one metal that is able to promote reductions, because what's happening is that here in these cages is going to happen oxidation and reduction. Oxidation, we will form oxygen. In reduction, we will form the reduced hydrogen, oxygen and hydrogen. And if we put this co-catalyst, we promote here the generation of hydrogen. And with this other co-catalyst, we promote the generation of oxygen. That is the most difficult reaction. So with this, we can also increase the activity. So just to make the story short, I will tell you one of the examples in where we have the highest activity. We have new examples with higher activity, but first we want to patent them. So this is IEF 11. This material was prepared here in Madrid. In Madrid, the particle size is very small. But they have been able to resolve the structure of this MOF by single crystal XRD. It's not possible, but by electron diffraction. So we know that the structure of this MOF is like this. This is the structure of the MOF. When I saw this, I said, oh, this is beautiful. This is what we wanted to have. We wanted to have a 2D titanium dioxide, 2D. We want to have layers of 2D titanium dioxide connected. And this is what really gives us the MOF. So there are 3 different types of titania, one titania here in the tetrahedra and 2 different octahedra. So we have 3 different types of titania. And the linker here that is very simple. This is squaric acid. It's very simple, but it's red because it's aromatic. It meets the Huckel rule. So we have 2 electrons in a cycle. 2 electrons in a cyclic compound, this is aromatic, so it's very stable. Even though it's 4 member rings, it's stable, and the important thing is that it's red. It's red because there is like a deuterium. So we have negative and positive charges. So organic chemistry is able to do this. And then we have something very simple that is red. So here what we have in this material is layers of titanium dioxide that they are connected here with the linker. Here is the linker. So if we excite the linker in the red, then we can promote the electron transfer to the titanium. And one interesting thing here is that for producing hydrogen, we need a reduction potential. The reduction potential at neutral pH is about -0.5. To produce oxygen from water, we need an oxidation potential. The oxidation potential that we need is about 0.8. So we need to achieve these potentials to promote the reaction. So with this material, this is the band gap. And this is the alignment of the bands. So this material is almost perfect, because the electron here will be able to reduce. The hole here will be able to oxidize. So with this, we can produce, this is the amount of hydrogen with sunlight, the amount of oxygen. The material is stable. Stability of this material is remarkable. This is the solar spectrum in where we don't have UV. This is compared to the xenon lamp. Xenon lamp is here. With xenon lamp, we almost produce the same as the sunlight. This is remarkable because instead of using a lamp, we are using natural sunlight. And with natural sunlight, the production of hydrogen is almost the same. The production of oxygen is, even in the visible, even if we use ambient light in the visible, we can also produce hydrogen and oxygen. The material is stable and does not degrade. So here is our target. Our target is a solar energy to hydrogen efficiency about 5%. So 5%, consider that photovoltaics are able to convert sunlight into electricity with an efficiency of 25%. So we are not asking that much, 25%. We are only asking 5%. If we reach 5% with a cost of €5 per kilogram, and the material is stable and operates per 1 year, so then we have something that can be applied. So companies, if we have these materials, the companies can apply it with these numbers. So how far and how close are we now? So in Japan, Domen is already now preparing pilot plans to show that these targets have been achieved. Our materials, they are stable for 1 year, the cost is reasonable, but the efficiency in our case is still a little bit lower than 1%. But this is not that difficult. We can improve, we can make a big jump if we just touch the right thing in the material. It's just a matter to introduce and to prepare the right material. So lower than 1% to have a 5% is not that different. Moving faster to CO2, the problem of CO2 is that compared to water, we have many different products, so selectivity is needed. Actually, the best product from CO2 will be methanol, but also formic acid is interesting, and also methane. So several products are possible in this case, and the most valuable products are methanol or C2 pros. The efficiency is much lower than overall water splitting. So for this reason, what can be easily predicted is that first, photocatalytically, we will produce hydrogen, and then later, a few years later, we will be able to reduce CO2. I will comment on this reaction that is methanation, because industry, they have capture and utilization of CO2. And the reaction that industry, thermal catalysis, wants to use is this. But this reaction that the industry wants to use can also be done photocatalytically without burning fuels. So our contribution to this area was to show that we can reduce CO2 with materials. This is the MOF, and the MOF contains this linker. This linker is bipyridine, and this linker bipyridine is very good to make a complex, and actually we just trying to mimic this molecular catalyst that contains ruthenium and rhenium. This molecular catalyst is able to reduce CO2, and we can produce the same similar catalyst in the MOF. How? We can just bind ruthenium in this, and we can bind rhenium in this other. And this material that is ruthenium and rhenium is more efficient than the molecular catalyst. It's more efficient than the molecular catalyst because this does not degrade. The typical degradation of this material is just because they lose the linkers. But here, because they are immobilized in the solid, there is no loss. And the last slide, this is photocatalytic nitrogen fixation. Is again, industry is doing this reaction in very large scale. This is the Haber-Bosch synthesis, and also without heating. So we can do the same process, we can do the same process, but without heating, just using sunlight. For this, we use a material that is strontium titanate, and these are the images of the material, strontium titanate, and with this, we can provide ammonia with light. This is the production of the ammonia, depending on the amount that we have of ruthenium. So with this, we reach the conclusion. So photocatalysis, how far, how close? Photocatalysis, the technology readiness level is about 3. So we are still far from any potential application. But if we make a jump, and this jump, there are many laboratories trying to do this jump, then we can be close. We know exactly what are the targets. The targets for this is 5% efficiency. I should mention that natural photocatalysis, the efficiency is 6%. So natural photocatalysis, and life has developed on this, has an efficiency of only 6%. So here our target is 6, and photocatalysis of CO2 is more difficult, and we are just progressing in photocatalytic nitrogen reduction. But still the efficiency is low. And with this, I want to finish thanking people that has contributed to the research, thanking funding agencies, and thanking you for being here.
Thank you, Hermenegildo, for this beautiful presentation. I hope you will get very soon the target of 5%.
Thank you, thank you.
And we have some time for one or two questions. Olga.
Yeah, so thank you for this excellent talk. Sorry, thank you for this excellent and very inspiring talk. I have a question about the solar spectrum is also rich in UV photons, and I'm wondering about the stability of the organic part of your system. So how do you see the long-term stability of these products?
Yes, this is a typical question in MOF, yes, stability. So if the reaction works well, if the electron transfers from one place to the other, and then we have the hole in the linker, if this hole is able to react very fast with water, then stability increases. But for those systems in where the hole remains there, so then at the end it reacts with oxygen and other things. Yes, so let's say that if we drive the reaction that we want, and stability increases. If we don't drive this.
As you said, it is really related to the number of defects, and the hole can be trapped by defect in the hole can be trapped by defect in the system, and then okay, on the long term, the system is likely to degrade.
Yes, yes. We publish a paper in where we expose 2 months, to the UV, and we observe the evolution of CO2. But with solar light, in 2 months, there was no. This was published in Angevante.
Last question.
Thank you very much. Actually, I have two points. So, in the first slide, in one of the first slide, you have shown the exponential grows up of the CO2. To get the net zero request, we should, in a way, spend or have a project that will spend exponentially in the same manner in order to get the net zero, which seems to me really challenging. And the next point is that, if you can comment, please, what will be the impact on the technology that you have presented on the actual infrastructure that transport the electricity in our country? Thank you.
Yes, so photocatalysis as photovoltaics requires land. We need 1 kilometer, square kilometer, something like this. Of course, we have to use the land because the sunlight, there is no other way to capture. Yes, so it's very similar to photovoltaics, except that our technology will be much cheaper, in the sense that we don't have silicons and other things.
Okay, then we should thank the audience.
Thank you so much. Good morning, everyone. I'm afraid and I thank Professor Ciencias for giving the introduction to this, but I should admit here, unfortunately, the problem is far more difficult, though, we all know. What we're talking about is a massive amount of CO2, a massive amount of water vapor in the atmosphere. What we do have another problem, which is how does this all is interconnected? And it's a lot interconnection in this. So, and I'm asking the question, how are we going to solve this from the educational point of view? We need to teach the next generation of chemists and scientists and how to tackle this. And that's why I come up with a question, what are the expectations of chemistry in general? And I can assure you, these are the 3, which are not all, but these are 3, which will play a role. Sustainability, which means, I will show you in a second, it's not only chemistry, it's interconnecting things a lot. It needs to be greener, which means avoiding toxic compounds, and molecular prediction, or in general prediction. So this makes the difference between science and theology, right? And we all know that chemistry is a central science. What does it mean? It means things are all connected, and we live from that. Now, sustainability is a broad term. It encompasses so many different things, you know, from economics to engineering, social science, etc. So all of this, right, impact. If you have part of that, the chemistry, we're talking about sustainable chemistry. That means we're talking about green chemistry. Green chemistry means to avoid things we're going to have to clean up when we have done all this afterwards. So why not taking this into account in the very beginning? So green chemistry has fortunately some rules, and people can recall this. But let me pointing out here, there is this seminal work by John Warner and Paul Anastas. They define what green chemistry is. There's sometimes confusion. People say green chemistry because it's a green party. No, it's not. Green chemistry means the design of chemical products and processes to reduce or eliminate the use and or generation of hazardous substances. Because at the end of the day, we will all eat this or drink it. So we don't want. We want to survive. So fortunately, this is all condensed into the 12 principles of green chemistry, defined by John Warner and Paul Anastas. You see here it starts from, it's arbitrary. You can start from 1 or you can start from 12. It's all interconnected, which means how we're going to use resources in all respect, very responsible. And we love to do catalysis because catalysis is spread out in so many different areas in chemistry, in physics, and engineering, so we should combine this. We should basically take the best of the worlds we know, in order to improve. Let me give you an example. We talked about, we're just here listening to the electricity price, okay? Let's assume we can all this do with photovoltaics. Silicon. The basis, the material basis for this is a huge carbon footprint, because if you see here, if you make PV panels, you have to make silicon. Currently, all the panels, all the electricity that comes from there has a huge carbon footprint, because the reaction is that we take sand, in a way, SO2, and reduce it with carbon, producing CO2 and silicon. So let's take these numbers. 7 million tons of silicon in 2018 had a direct emission, only a direct emission of 11 megatons of CO2. That means we are here stuck. We have a problem. We sell on one side, oh, cool, we have the photovoltaics, we can solve all the problem, but the silicon basically comes from there. So, of course, we can recycle, we can be doing better, and so on and so forth, but why not trying to do this in the very beginning differently, though? So this is the junction to change, not only one, but there's another junction to change, to think about how could we produce silicon away from thermal emission, away from thermal chemistry, using electricity. There's this very nice paper I refer to Alan Bart, who suggested to do this reduction, electroreduction of SiO2 with electricity in order to make silicon and oxygen. But look at this, the temperature is terribly high, 850 centigrade in molten calcium chloride. Well, that's a starting point, isn't it? So now there's plenty of things for the next generation of chemists. I'm not worried about there are not enough targets, right? So this is one of the big targets we are ahead of us. Now get to the point. What I think is important, and that has been pointed out by the previous speaker, we need to learn more how to make excess of the excited states in molecules. Basically, thermal chemistry is ground state chemistry, right? It's like if you get up in the morning, you get a coffee, this is our ground state thing. But we can look at the sun and we get excited and our brain starts to think. That's basically the comparison to here. So molecules can get up electrons, excited electrons. And we've studied this in Berlin for quite a while. And we call this the unifying systems in catalysis, where things are interconnected, but using energy different from the fossil resources. And I refer you to this website if you're interested in this. Now, we published a couple of years ago a paper where we said, okay, there's of course this problem out there, CO2 reduction. But I should make a remark here, CO2 reduction, we're talking about a huge amount of CO2, right? Even if it's diluted in the atmosphere, if you capture this, who's gonna using that amount of CO2 and making methanol? Nobody. So that means we need to avoid to emit CO2 in the first place. We need to basically make circular chemistry in the first place. And we need to learn all the protocols. Actually, the good news is the chemistry is known. The bad news is there is a missing junction in the energy transfer, what we also learned. What are the catalysts doing that? And everybody should do it, not basically depending on the resources, Western world or Eastern world or whatever world. So we are unified in that kind of problem here we face too. So we thought beyond CO2 reduction, which is already an issue, we're dealing day by day with things like reduction of other metal oxides, which are also very poor in energy, not only CO2. And I refer you to the bond energies here, where we talk about CO2 bond energy, 799 kilojoule per mole to basically, disconnect. You go to other elements, silicon oxide is not far away, as we said, silicon dioxide reduction, silicon, or phosphorus oxide stuff. So these are a lot of things out there which are needed in order to make our world as it is, with starting materials. So this is not the only thing we are faced to. And I would like to give you an example what we have studied, and I think it's an example which is a learning case perhaps for others. So let's take this reaction. Phosphorus oxygen double bond is almost as strong as a carbon oxygen double bond. We heard about this, CO2 to CO, everything would be great. Here the problem is we need to inject 2 electrons. We need to inject 2 electrons and then get rid of the O2 minus, and all is good. So this is basically done on the basis of thermal reactions. And you ask yourself, what in the hell is interesting in doing this kind of chemistry? Here's the example. There are industrial cases which are not unimportant, I would say. Let's say the synthesis of vitamin A. I don't know whether you took the pill today or tomorrow or the day after tomorrow. It will come. And it's an additive or a nutrition stuff. So this is a reaction. Sorry about the details. If you're not a chemist, don't worry. You basically couple a carbon phosphorus bond with a carbon oxygen bond, and you make this kind of reaction here. So we basically have partner switch, right? Where we have phosphorus is taking up the oxygen of the carbonyl, and carbon-carbon double bond is formed, and we have the formation of this carbon-carbon double bond. This is a very important reaction, has been recognized with a Nobel Prize. It's called the Wittig reaction, Wittig olefination reaction. And you see here, we transform originally the phosphine, which is needed to do that, into phosphine oxide. And of course, in order to be productive here, we need to come back. We need, first of all, to remove the phosphorus oxide from the reaction mixture when you have done this. And then we're going to recycle the phosphine oxide to phosphine. Now, it's an important thing to remind us that in engineering, most reactions we do in the lab on a small scale do not survive in industry. I mean, do not get upscale. The reason for that is separation costs. We heard about this, cost. Everywhere people are asking for how much does it cost, and so on. At some point, it's not a matter of the cost because it's unavoidable. I would say the problem with the CO2 and the water and all this kind of thing. This is a weird discussion saying how much does it cost to make this and this and this. If you cannot survive, I think we will spend all what we have. Here, it makes sense to ask about the costs. And of course, the costs here are basically defined by the process and the value added you're producing here. Just to give you an example, removing the phosphine oxide from that is an issue. And it makes about 30% of the cost for the process, okay? So therefore, research has been spun on this. People have tried that. And once you have the phosphine oxide back, you reduce that. And what you basically do is you're using chemicals which are very electron-rich, silanes down on the left side in the corner, silanes, boranes, and so on. So basically, they're taking up the oxygen, leave behind the phosphine as you want, but then the oxygen is basically making another type of waste. You want to avoid this. And, And if you, there are other processes, let's say industry developed, where they're using poison stuff like phosgene, unfortunately, and give rise to that reaction here, where you're actually using a sacrificial agent. You're using aluminum in order to get rid of the oxygen. So somebody in this reaction, some guy, takes the oxygen over, and you basically postpone the problem into another waste problem, right? So therefore, this is what we're basically doing, cheating all the time. You know, you're selling some things that I solved the problem, I give the problem to the next generation. That's what we basically do. That's very common. Now, this is the solution. I would say the solution is you're using not sacrificial agents. You don't postpone the problem. You basically use electrons in order to liberate the oxygen from the phosphorus oxide, and that gets away as O2 minus. Similar, the oxide anion, similar to what is in water. And this has been, well, of course, this has been developed. There are people who have been looking at this. But again, you can do that electrochemically by using sacrificial anodes, like say aluminum. So similarly, so you're ending up with this kind of waste. However, the costs for that are lower because you do not work on the separation thing here necessarily. So all this type of variations have been developed. And so there's an interesting concept which caught our attention. That is, if you take the phosphine oxide and this double bond, if you lower the bond energy between the phosphorus and oxygen bond, using a Lewis acid like boron, then you can basically shift the electrochemical potential to lower energy in order to facilitate the reduction. And this has been applied to my dear friend Dan Osera. And he has shown that you can basically do this on a reasonable scale. Now, and there are versions of that, again, all dealing with this type of sacrificial agents. Now, here we come. What we had in mind is not only to do the phosphine oxide reduction, but to keep the whole process in a cycle, right? To make a chemical cycling process here out of this. And I call this, it's a system, it's an electrocatalytic system where you basically have different types of partial reactions. So first of all, we reduce the phosphine oxide to phosphine. We use the phosphine in order to make the Wittig reagent. And the Wittig reagent is then exposed to the carbonyl in order to make the desired carbon-carbon coupling process. So if you are manageable to do that, and by the way, you cannot do this in one part, in one shot, you basically need to discontinue doing this. That works. So I wouldn't stand here if this wouldn't work. These are the research questions. Can we do this overall electrochemically? The answer is yes. Now, why is that possible? And you have to obey a couple things. First of all, the problem in this is the phosphorus oxide double bond is very strong, 544 kilojoule per mole. Compare this to the phosphorus carbon bond in the molecule, it's half of all this. Therefore, if you do it not correctly, if you look at thermodynamics only, you're cleaving the phosphorus carbon bond. That's why this is a failure. In order to avoid this, we're using an organic Lewis acid. This is a guy who basically jumps on the phosphine oxide and lowers the phosphorus oxygen energy. And we're using a Lewis acid which can also be produced in a sustainable manner. You produce that by electrochemical methods, and you can basically recover this by electrochemical methods as well. We're using a methyl cation. This is academic methyl triflate, but you can use other types of Lewis acids. But just to show you the principles, it's enough here. So basically, this jumps on this, and you're making, you carbonylate the oxygen here. You make a cationic molecule. And the cationic molecule now is ready to take up electrons. As you heard, cations love electrons. So if you put an electron to the phosphine oxide, you gain basically just a little bit of energy. Whereas if you provide a positive charge because you added the methyl cation, methyl here, you see here you gain a tremendous amount of energy. Well, that system is ready to swallow electrons here. Therefore, we're going in the right direction. Now, you can do, very easy, everybody can do. A customized electrolysis cell is very simple. So basically make, first of all, the methylation. This is, you can look up this phosphorus as protons have a nuclear spin. You can do the NMR spectroscopy here. It tells you there's a tremendous shift here because of the methylation. But more important here, look at this. This is a cyclovotomogram, which shows you the shift. The electrochemical shift is dramatically lowered by 870 millivolts. This is substantial, which means this is now a feasible process for going on to this reduction. Now you do this and you take an electrode. So this is an anodic process. We're using a silver of the one side. and as an anode, and platinum at the other side. And you're using acetonitrile because if you would use this water, and you would do this in water, you would compete with the reduction of protons in water. You would produce hydrogen. You don't want that, okay? You do this, you're ready, and then you see, okay, it's half good. It's only 39%. You're producing, the fate of the methyl, of this group here is to produce methanol. Methanol can be easily be recycled back to the starting material where we methylated. So this is, by the way, something which is great. But you see here, you reproduce the phosphine oxide. What's the problem? The problem is kinetic barrier. Once you have reduced that guy here, and you give 2 electrons, the methyl oxide is very lazy to go away. So you need some incentive that the methyl oxide anion is taken away. And this is also thermodynamically, you can easily explain. And I don't want to go into details, but just let me point you out, there's another thermodynamic problem. So you get rid of the methyl oxide, you gain minus 50 kilocalories per mole, but you also can lose, you can break the carbon-oxygen bond here, and then you gain 45 kilocalories per mole. This is close. Well, therefore, we have this competing thing. Therefore, hey, we need a catalyst. We need somebody who's helping in this, right? Jump on the oxygen in order to remove the methyl oxide group. So, Lewis acid assisted is it called. This was the first attempt here, and we were looking around, and cut a long story short, we found this, for you probably exotic scandium triflate. Scandium, it's a lanthanide, it's a redox innocent cation. So it does not interfere, does not take up, does not eat electrons here. It jumps on the oxygen, and it basically weakens the phosphorus-oxygen bond here, and then you get this. You see, we jump up to 79%. However, the problem is we need almost a stoichiometric amount, 0.6 molar equivalents. That's not good. We have another separation problem here, right? Although we reached what we wanted to, we had this kind of biased situation here. Now, but it was good to demonstrate this is not a bad idea to go along these lines. So we did all this in a cycle, scandium triflate, all this kind of thing, and we injected step by step. We have a robot which can do that for us. You get monitoring. So you have this kind of discontinuous process in producing organic chemicals. And this was a paper we published first, where we showed we can make carbon-carbon bond formation, and even this tolerates functional groups. So not that simple compounds, but more complicated compounds. I can assure you what we wanted to make is vitamin A, right? So it was a way to go in achieving this. But first of all, what we also thought is we need to replace somehow the scandium. The scandium is not sustainable in this. It's too high amount. And we looked for other Lewis acids, and we observed, to cut a long story short, if we add to this as a Lewis acid tin triflate, tin 2, it's a salt, easy and cheap and so on. We realized that if you take platinum electrodes and you put this tin triflate in the solution, on the electrode, on the anode, tin is basically precipitating, depositing. So the anode is a shiny metallic silver, and if you run the process, you take out the electrodes, it's black. And if you analyze that, it turns out it's simply tin. I said, wait a minute. If tin does this on the platinum electrode, do we really need platinum? The answer is no, we don't need. So because we can deposit this, we used tin foil. You go to the supermarket and you buy the foil. You use usually aluminum tin foil, right? And you can use it as an electrode. Now we go. We have this dual function. The tin is there, it does its job, but it doesn't come off, right? So therefore, that's all what we wanted. It's just dream-like. So we can do that. And now look at this. The yields we can achieve here with the tin foil is 92%, with a ferritic efficiency of 79%. That's fantastic. But therefore, just by chance, just by luck, okay, experiments, you have to do. You know, the success increases by the number of experiments, not by talking, doing it, right? So here we go. And we will pass it, and I don't want to share all this kind of thing, the details, but I can assure you it's a very complicated thing. By the way, the tin oxide can also be used for for the CO2 reduction process to CO, has been invented. So this kind of thing is very, very nicely. So now we have this optimum, we believe, and this gentleman says, come on, let's make vitamin A with this, right? So That's what we basically did. We can go all the way around there, right? You are not all of you chemists, so we made this, the Wittig Ulit, right, in situ, have the tin anode, and we can do all this coupling thing. We can also make some compounds which have some importance, for example, as drugs. So my colleagues, my beloved colleagues in organic chemistry said, oh, why don't we do this kind of interconnection thing? Yeah, good, let's do it. So this is an entry, and we were happy that we could do some contribution in this here, but finally, we're able to make this guy here, right? So this is on the basis of this tin electrode, we were capable to make that product, which is made on the ton scale in BASF, in other companies, and at one day you will swallow it, right? So, and I think this is a good thing to do, and has implications as a role model, perhaps, to go on with other type of reduction processes. Now, what is the future? The future is we're gonna use the electrons. The electrons should come from somewhere. From sustainable resources like this one here, sugars or wood, whatever we have, right? We do this biorefinery kind of thing. There's a lot of people doing out there. And the electrons from this process, from this oxidation process, are transferred on the other side with a tin foil, and we do this process. So we're basically pairing this up. We do on one side the vitamin A thing, on the other side we do some added value production. This is on its way. We published a couple things on that, we patented a couple things of that, and this is how the future looks like. You're harnessing on one side the organic stuff, and you combine that, and so on. So this is how we work. Everything is interconnected. Nothing stands by its own, right? That's the future. And I thank you so much for listening. Thanks.
Thank you very much, Professor Dries, for this very interesting presentation, opening windows on the future. Are there one question, maybe?
Thank you very much. You, at the very beginning, you spoke of new generation of chemists. Do you have any syllabus for them?
Absolutely, yeah, sure.
You didn't show?
Yeah. Well, 25 minutes. That's the price I'm going to pay for it.
Okay.
But it's for sure. I think this is something we forget, right? We're talking about papers, we're talking about success of the individual, all this kind of thing. No, the future is people. The future are people. So if you do not educate the people accordingly, nobody will do it. So I think there's a long way to go. How are we going to teach chemistry? How are we going to teach physics? What is the interconnection here? Biology, all this kind of thing. Well, this is what we do in the cluster of excellence. It's the Esperanto.
That would be very interesting.
The Esperanto. Be neat.
Okay.
Okay.
Thank you.
Thank you.
Thank you again.
Thank you.
Hello from Madrid. So, do you hear me?
It's good for you?
Okay. So, I welcome you from the Royal Spanish Academy of Science in Madrid for the Symposium of EurASc devoted to the new way for getting energy. And so you are Professor Claude Grison, Director of the Bio-Inspired Chemistry and Ecological Innovation at University of Montpellier, France. And you will present the future of catalysis and energy in your talk, 20 minutes talk plus 5 minutes discussion on eco-catalysis and nature for the future. So please, Mrs. Grison, could you start?
Many thanks for your introduction, and good morning, everyone. I would like to thank the Scientific and Organizing Committee for the invitation at the International Symposium in Madrid. Facing global crises as to climate change, pollution, biodiversity erosion, and limited resources, promoting scientific exchange about sustainable sciences is important to build a different future. It is clear that new ways of thinking are needed to provide concrete solutions. And it's a great pleasure to share the concept of eco-catalysis that brings together chemistry and ecology to create these solutions. In December 2022 in Canada, governments from around the world came together to set new goals to guide global action to halt and reverse natural loss. 5 drivers of the natural crisis have been identified. The first one is how people use the land and sea. This includes the conversion of forests, wasteland, and other natural habitats for agricultural and urban uses. As you all know, for 40 years, greenhouse gas emissions have doubled, causing a global warming which is affecting species and ecosystems around the world. The recent IPBES report has revealed that the unsustainable use of plants and animals is threatening the livelihoods of billions of people. We relied on wild species for food, fuel, and income. Pollution, including chemicals and waste, is a major driver of biodiversity and ecosystem change, with especially devastating impacts and direct effects on both freshwater, soils, and marine habitats. Finally, invasive alien species are animals, plants, fungi, and microorganisms that have entered by human cleanliness outside the natural habitat. Alien invasive species have devastating impacts on native plants and animal lives, causing the decline and even the extinction of natural species. My team has chosen to take a strong commitment to major challenges. The first one, the pollution, soils and water pollution. And the second one is the uncontrolled development of invasive alien species, including plants and insects. Why? Because we call for more invention in green chemistry. How can we take up these 2 challenges? I think that the development of the nature-based solution as defined by IUCN can address this need. They can serve as a basis to these issues of pollution and development of invasive alien species through action of protection and restoration of degraded ecosystems. However, the sustainability of the nature-based solution is subject to 1 condition, making this solution economically viable. What are the nature-based solutions to the problem of land ecosystems, which are contaminated by metallic elements? The guideline of our strategy is based on the concept of ecological restoration, thanks to the remarkable adaptive capacity of specific land plants to metallic stress. Some specific plants are able to survive in contaminated soils and to hyperaccumulating metals into shoots in high concentration. This natural phenomenon is called phytoextraction. We have demonstrated the performance of this technology, this phytotechnology, in different on large scale and in different countries, such as France, Greece, China, Gabon, and New Caledonia. Bringing an economic dimension to this phytotechnology was essential. To do so, we have developed the first chemical recovery of the biomass, subsequent biomass. Leaves enriched in metallic elements are transformed into metal catalysts, the first biosource metal catalyst for the organic chemistry through the preparation of molecules of high added value. The first regeneration of eco-catalysts has revealed the possibility to combine in a single catalyst branched acid, hard Lewis, and soft acid properties in the single eco-catalyst. We have demonstrated the interest of these properties in different mechanisms on green chemistry, such as multi-component reaction, cycloadditions, and domino reactions, allowing the synthesis of numerous heterocycles, such as thiopyrimidines, benzodiazepines, dihydropyrimidines, substituted triazoles, lactone with chiral group, cannabinoids, chromens, furanoic acids, which is chiral groups, and capped RNA. Two types of reductions have been investigated by ecocatalysis: the direct reduction and the amino reduction of carbonyl compounds. The regioselective reductions is catalyzed by eco-nickel, completely biosourced eco-nickel, where nickel is at the zero oxidation state. This eco-catalyst allows the hydrogenation with isopropanol, an eco-friendly reagent and solvent. The regioselectivity of reduction of unsaturated aldehydes and ketones should be noted. This performance can be explained as a particular structure of eco-nickel, which is composed of an unusual salt, namely iron nickel 3. And these results constitute a valuable alternative for the reduction of these carbonyl compounds to classical catalysts based on precious metals. Amino reduction of carbonyl compounds is catalyzed by ecomanganese catalyst, which constitutes the first example of reduction with the manganese promoter. The reduction is conducted without solvent with the easily prepared and safe orange ester as reducing agent. This methodology was applied to reductive amination of various ketones, including to precursor of pharmaceutical active compounds. A wide range of ecomanganese have been described for oxidative transformation, such as epoxidation, oxidative cleavage of diols, alcohol oxidation, and oxidative iodation. The particular structure of this ecomanganese, called eco-CA-MnOx, close to the natural cluster of photosystem 2, should be noted and allows the preparation of sensitive epoxides. Finally, ecomanganese catalysts can act as Janus catalysts by promoting tandem sequences of multi-component reactions, types such as oxidation carbonyl reaction and oxidation cyclization. Finally, this ecomanganese catalyst can be excellent substituted to oxidant, which is regulated by which regulation. How useful is this research? Today, at the present time, this research as a starting point of a large industrial project in New Caledonia, combining the ecological restoration of mining sites with manganese and nickel accumulating plains. This effort of ecological restoration is associated to the recovery of our lead plants in mining restoration. There is plants which accumulate manganese for the synthesis of biomimetic oxidant called eco-CMNOx. The eco-catalysis concept can now be extended to variable and abundant aquatic plants, which are able to phytoaccumulated metals quickly into roots. The combination incorporating rhizofiltration and eco-catalysis is a real opportunity for the development of a new generation eco-catalytic materials. This tandem is attractive in terms of chemical biodiversity. It overcomes the limit of phytoextraction and gives the possibility of preparing of the first eco-palladium. The rhizofiltration mechanisms of metallic elements were studied in depth with floating plants. We have discovered that the traffic of metallic elements by roots relies on the peculiar chemical structure of the roots rather than on the physiological process of the plant by itself. It was thus possible to directly use roots from dead aquatic plants to transform roots into a fine powder for the design of plant filter to clean up polluted water in different scenarios. The first scenario is recycling of strategic metals such as palladium, platinum, and rare earth metals, and volatile metals such as scandium, primary metals such as manganese, nickel, copper, zinc, and iron, and toxic elements as defined by the European REACH regulation like arsenic, cobalt, lead, and cadmium. Rhizofiltration and biosorption led to a new generation of eco-catalysts capable of catalyzing Lewis acid reaction, oxidation, and reaction with selectivity specificities. Thanks to rhizofiltration and biosorption, for the first time, it was possible to promote cross-coupling reaction with eco-copper, eco-palladium, and eco-nickel catalysts. For the Ullmann coupling, Suzuki, Sonogashira, and Heck coupling reactions. The best results were obtained with eco-palladium eco-catalyst. We can explain these results by the specific morphology of eco-palladium, which is composed of small nanoparticles between 2 and 4 nanometers, which are stable, non-aggregated, and well dispersed on the mineral matrix of the eco-catalyst, which is composed of cations, physiological cations of the plants. These coupling reactions worked in green solvents, glycerol, butanol, water, in moderate reaction time and temperature, and without ligand, co-catalyst, or additive, allowing an easy recycling and reuse of eco-palladium. What is the use of this research? These researchers are applied in two contexts. The first one is the ecological recycling of strategic metals from industrial effluents in close collaboration with chemical industrial groups. And the second application in the preparation of pharmaceutical products which have required the palladium-assisted catalysis steps. We can consider that eco-catalysis is an effective solution for the depletion of flavonoids with significant environmental benefits. Remember, invasive alien species have devastating impacts on native plants and animal life. 60% of extinction species are due to the invasive alien species. Fallopian japonica is a demonstrative example of this problem. These plants has invaded many countries in Europe, and my team is studying a new management of Fallopian japonica. Instead of extracting rhizomes, which requires considerable efforts with questionable results, repeated and massive harvests of aerial parts can affect the vegetative dynamics and the plants and help to recreate habitats for native species. The harvested aerial parts, instead of becoming waste, can be valorized and used in eco-catalysis concept, becoming an innovative short to medium-term response to support new way of managing invasive alien species in wetlands. The other generation of eco-catalysts is very useful as base catalyst and able to promote transesterification, cascade reaction, oxidative esterification, aldolization, quatonization, and Michael addition, and tandem sequences of this reaction. This development is carrying out on large scale and open a vast field of application in organic chemistry. Resulting metal rich from this biomass is a real opportunity in green chemistry and led to the creation of bio-inspired company to exploit these invasive plants and produce biosourced molecules. Certain processes have obtained different biolabels, such as Cosmo-Organic, as defined by EcoCert. We can consider that the chemical activities support the sustainable management of the preservation of wetlands. Another problem is the development of invasive insects, such as mosquitoes. For example, Aedes albopictus came to Argent tiger mosquitoes. Is a real Earth problem because mosquito-borne disease currently accounts for 70% of infectious disease. The progress of these mosquitoes is constant and worrying in France and in Europe. To progress against the protection against these mosquitoes, we considered that the complexity of receptors of mosquitoes should be taken into account. This analysis led to a new hypothesis of research that the repulsion should be based on similar molecular mechanisms to attraction. For test this hypothesis, our strategy was based on 3 steps: target multiple receptors to maximize repellency, identify combinatorial interaction between natural molecule odorants with receptors, and synthesize the ideal molecular combination with a natural process. It was thus possible to find natural solutions that were more repellent than those on the market. What's the use of this research? After 3 years of intense research, this solution was marketed under the name Crusoe by Laboratório Bioprotection. Do not hesitate to buy a Crusoe in pharmacy, parapharmacy on the internet. I hope that I have convinced you that the combination of ecology and chemistry can be very positive. Ecology allows the development of nature-based solutions to solve different environmental problems, such as pollution of water, soils, and the uncontrolled development of invasive species. Thanks to eco-catalysis, green and sustainable chemistry is a driving force of ecology. The presentation time was short, but you can find details of this works in the forthcoming book that's written and the invitation of the Royal Society of Chemistry. Many thanks for your attention.
Thank you very much, Professor Grison, for this very interesting talk, showing us the importance of this new generation of eco-catalysts for recycling strategic metal and also for solving some problems of invasive species. So I think the audience has been very much interested, and we'll have some questions. So, Mr. Porter.
Yes, thank you very much for your talk. It's very interesting and inspiring. And one of the subtexts of our symposium is science multidisciplinarity for the 21st century, and I think that's a wonderful title. And I was thinking, how could your research be put into a multidisciplinary background? And one of the things I was thinking about is, what is the relationship really between what you're doing and what ecologists call ecosystem services? Because you are, by using these technology, generating a certain number of ecosystem services. And this could be actually put together to add another dimension to your research. So that's one question. And the second question I have is, when you say economic viability, what do you actually mean by that? Because that also impinges on what do we value here? What are we valuing here? And if you were a game to introduce ecosystem services, then that would be a different kind of valuation from straight economic viability, for example. So those are my two questions. Thank you.
Thank you for interesting questions. The sound quality is poor, and I hope I have answered these questions. The interdisciplinarity of my work is an essential condition to success, and my team is composed of chemists, ecologists, and the interaction between ecology and chemistry can be very useful. And I hope that I have shown the problem. The knowledge in ecology is a source of innovation and chemistry, and is essential to understand the physiological process of these plants, to develop with success the concept of eco-catalysis for chemistry. Interaction were essential. And the economic development of eco-catalysis is a reality because we have created bio-inspired company, and the scheme of the economic dimension is based on the value of chemistry. Bio-inspired company is producing biomolecules, and the market of biomolecules is an opportunity to support the financial efforts on ecology.
Okay. Thank you very much, Professor Grison, for this excellent answer. Are there last question in the audience? Okay. If not, we thank you again very much for this fantastic presentation.